Hello students, the discussion today is about one-way analysis of variance, or in short, one-way ANOVA. We do one-way ANOVA when we have to compare more than two means at a time. If you still remember factors of experimental designs, then one-way ANOVA is to analyze designs with a single factor. We know the levels of the factor for a single factor experiment are also called the treatments. If the experiment has more than one factor, each factor can have multiple levels, and then each combination of factor levels is called a treatment. In one-way ANOVA setup, we analyze only one factor experiments. That sounds somewhat primitive. However, even if you have more than one factor, the respective combinations of levels of all the factors as a whole can be modeled as treatments of a single factor. Therefore, one-way ANOVA, even though it's somewhat primitive, it's still a powerful tool that can be used to analyze a wide range of experimental data. For example, if you want to see if the exam performances of students are affected by the number of hours that they work, the factor is the number of hours they work. It can have several different levels. For example, lesser than 10 hours, 10 to 20 hours, or over 20 hours could be the levels. If you have only that factor, then these three levels are also called the treatments. If we need to analyze this factor, we will have to compare three means at the same time. You may have some other factors also which may affect the exam performances. For example, the number of total credit hours taken could be a possible factor. That factor may also have several levels, such as lesser than 9 credit hours, 9 to 18 credit hours, 18 to 27 credit hours, and over 27 credit hours. If you classify it as that, then that factor has 4 levels. A formal definition of a factor is something that can directly affect the outcome or the response variable of the experiment. In this case, the exam performances. So the first factor, hours worked, had 3 levels, and the second factor, total number of credit hours, had 4 levels. If you analyze the data from both factors together, it's a two-factor design with number of treatments equals to 3 times 4, which is 12 treatments. One example for a treatment is working 10 to 20 hours and taking 18 to 27 credit hours. You can still model this as a single factor experiment as well. If you define a new factor called hours work and credit hours taken with 12 different levels. Either way, you have to compare 12 different means at the same time. So far, we have not discussed comparing more than 2 means at a time. However, you can see there are plenty of cases where multiple mean comparison becomes useful. This is the reason why we will discuss multiple mean comparison, and we call that process the analysis of variance. If some of these terms, such as factors, levels, and treatments, are not too clear, you don't have to worry too much to understand the stuff discussed in this lecture, since we will do only one-way ANOVA. However, if you want more information on those technical terms, you may watch the lecture video on experimental methods of data collections. All right, so the analysis of a single factor or one-way ANOVA is an important statistical tool. Note once again that for all experimental designs, a response variable is required. A possible response variable for the example discussed is the student GPA. In an analysis of variance study, what we do is to see if the factors affect the response variable. We do it by comparing the true means of response variable at respective combinations of factor levels, or in other words, by comparing the treatment means, which will eventually lead to multiple mean comparison. All right, let's discuss the details and see how to develop a test statistic for that purpose. All right, let's quickly see the importance of multiple mean comparison. Why we need a specific method for testing multiple means is because we need to control the error of statistical hypothesis testing. Also, we need an efficient method for the multiple mean comparisons. We know we pay attention on alpha, which is type 1 error. We maintained it at 5% in all the previous hypothesis testing procedures. Can we do it here also when we have to compare multiple means? Here is an example. If there are several brands of a type of product you need to introduce to the market, how can you compare that your product is at least equal to the other products in terms of product characteristics? Well, the product characteristics could be the price, durability, or any other quantitative or qualitative characteristics. You may do a t-test to compare your product with any other product in terms of a given specific product characteristic. But the problem is, if you have to compare your product with multiple other products already available in the market, then comparing your product with a selected one product from the market at a time using the t-test is inefficient. A collection of t-tests is not only inefficient. As you perform more and more tests, the error gets accumulated. The error will not be linearly added. For example, if you maintain an error of 5% per test, doing 3 tests doesn't mean that you accumulated a 15% error. However, it will be added non-linearly and it will be greater than 5% at the end. We have to avoid that. That's why we have a specific single test to compare multiple means, the analysis of variance F test, or in short, the Anova F test. We use the Anova F test to compare more than 2 means from independent populations. The data must be normally distributed. Remember that, it's important. The data must be normally distributed. The Anova F test allows us to control the error at a desired alpha, practically 5%. This means you can compare technically any number of means, maybe 10 means or even more. You can do it in a single test and the type 1 error is maintained at 5%. All right, we will now see how to write down the null and the alternative hypothesis for multiple mean comparison with Anova F test. We will let mu1, mu2, mu3 up to mu(n) be the true means from the populations 1, 2, 3 up to n respectively. Then the null hypothesis H0 is written as all the means are equal. You may write it in words as that, or if you prefer symbols, you may write it as mu1 equals mu2 equals mu3 equals all the way up to mu(n). The alternative hypothesis H1 is written as at least one mean is different from the other means. You can write it as that in words, or there is also a mathematical way to write it. However, I have avoided mathematical symbols based H1 to keep the discussion simple. Actually, writing down H1 as this will be the easiest. However, when we write down the null and the alternative hypothesis this way and perform the Anova F test, then H0, the null hypothesis, if rejected, we can only conclude that at least one mean is different from the other means. However, the test will not straight away tell us which mean or means is different from the other means. In that case, if the null hypothesis is rejected, then in order to decide which mean or means are different from the other means, there are separate other statistical procedures available, such as the Fisher's least significant difference, abbreviated LSD, Tukey's honest significant difference, abbreviated HSD, etc. However, we will not discuss those methods under intro statistics. I might post an optional lecture explaining how to use those methods, but I will not hold you responsible to work on it. Actually, if you compared a new product using a certain selected characteristic against the other products of the market using the Anova F test, and if the test signaled at least one mean is different, then it's most likely that the new product has the different characteristic. Survival of the market usually means all the products are almost equal. However, without doing too much of further analysis using any advanced methods, you may simply look at the summary statistics and also some graphical representations such as box whisker plot and see which mean shows a notable difference than the other means. Alright, let's now see the foundation for the Anova F test. As you saw on the previous page, the null hypothesis H0 for multiple mean comparison is mu1 equals, mu2 equals, mu3 equals, and so on up to all the number of available means to be compared. Let's now assume we have to compare 4 population means. That means we must have 4 independent populations. Population 1, population 2, population 3, and population 4. To compare the means which we don't know, we have to estimate them. To estimate the means, we have to obtain samples of data from each population. Let's say this is a sample of data collected from population 1. Here is a sample of data collected from population 2. Here is a sample of data collected from population 3. And here is a sample of data collected from population 4. We know how to calculate the sample statistics, such as sample mean, sample standard deviation, quartiles, etc. Let's calculate the sample mean and the sample variance for each sample. Remember that the variance is the square of standard deviation. If you use your calculator TI-84 to calculate the statistics, it will only report the standard deviation, which you have to square in order to obtain the variance. Alright, here is the mean and the variance for sample 1. Mean is approximately equal to 20 and the variance is approximately equal to 2. For sample 2, the mean is approximately equal to 30 and the variance is approximately equal to 2. For sample 3, the mean is approximately equal to 40 and the variance is approximately equal to 2. For sample 4, the mean is approximately equal to 50 and the variance is approximately equal to 2. Now, what do you think about these 4 means? What we have are the 4 sample means. What can you say about the 4 population means based on the sample means? Quite obviously, the population means are different. If we test the null hypothesis, mu1 equals, mu2 equals, mu3 equals, mu4 versus the alternative hypothesis, at least one mean is different from the other means. Quite obviously, the null hypothesis should be rejected. We can safely do that because the population means are clearly different. However, the population means being different is not enough. Another 4 samples obtained from 4 new populations may have sample means approximately equal to 30, 31, 32, and 33. Can't they be considered close enough? If we may consider those 4 as close enough, why can't we consider the 4 sample means shown on the screen as close enough? The answer to that question is the means of the 4 samples shown on the screen are more different than the variability within each sample. Or in other words, differences between means is much larger compared to the variance of the data in each sample or the differences within each sample. Because the means are different in tens, whereas the variance in each sample is approximately equal to 2. We can more clearly see this if we calculate the variance between sample means and compare it against the variance within samples. If we calculate the variance between samples or groups, i.e. the variance of 20, 30, 40, and 50, you can see that it will be approximately equal to 167. That variance is super large compared to the variance within samples or groups, which is 2. We reject the null hypothesis, which says all the means are equal because the variance between groups is larger compared to the variance within groups. How can we combine them and provide a single numerical value for comparison? We take the ratio of variance between groups and variance within groups. If that ratio is large, we reject the null hypothesis. Otherwise, the null hypothesis is accepted. To decide if the ratio is large or small, we need to figure out the distribution of the ratio. Then you have to compare it against a critical value from that distribution. You will see that the ratio of variance between groups to variance within groups follows F distribution. All right, let's see the Anova F test in details. All right, like I said earlier, the null hypothesis H0, which indicates that all the means are equal, should be rejected if the variance between groups observed through variance between sample means is high compared to the variance within groups observed through variance within each sample. To combine the two ideas, we take the ratio variance between groups to variance within groups. For the moment, we will label this ratio as F test. We reject the null hypothesis if F test is large. Why do we say this ratio is F test? We need something to recall from the very first week of the class and also from Instructors Chapter 2. We need the equation of the variance. Variance equals the summation xi minus x bar, everything squared, all divided by n minus 1. Now we need the distribution of variance. What is it? We will see it step by step. In the equation of the variance, the numerator is a sum of squares. The denominator is n minus 1. And the special name we use for n minus 1 is degrees of freedom. So we say the variance equals sums of squares divided by degrees of freedom. In short, you write it as SS divided by DF. The ratio of sums of squares to degrees of freedom is also called mean squares and is abbreviated by MS. Actually, the variance equals the mean squares. Now, what's the distribution of variance? It's easy to see the distribution of variance as the distribution of mean squares. We know x bar is essentially normally distributed according to the central limit theorem because x bar is the sample mean. If xi data points are also normally distributed, then we know xi minus x bar will also follow a normal distribution. If so, what's the distribution of sum of all n terms of xi minus x bar, everything squared, divided by n minus 1? As we saw in Instructors Chapter 2, this summation divided by n minus 1 must follow the chi-squared distribution with n minus 1 degrees of freedom. Now, if you look at this equation of F test again, we have a ratio between two variances, which we can write as sums of squares between groups divided by degrees of freedom between groups, all that divided by sums of squares within groups divided by degrees of freedom within groups. And that ratio is equal to the mean squares between groups divided by mean squares within groups. Or in other words, F test statistic is a ratio between two chi-squared variables adjusted for degrees of freedoms. What's the distribution of the ratio between two chi-squared random variables adjusted for degrees of freedoms? As we saw in Instructors Chapter 2, that ratio follows the F distribution with 2 degrees of freedoms, called numerator degrees of freedom, which is given as df1, and denominator degrees of freedom, which is given as df2. The numerator degrees of freedom, df1, is equal to the number of groups minus 1. The denominator degrees of freedom, df2, is equal to the number of data points in each group minus 1, and you have to sum them up. All right, now we know how to calculate the F test statistic. This test statistic should be compared against the F critical value. To find the F critical value, you have to use the traditional F distribution table. I think TI-84 CE Plus still doesn't have the inverse F function, unfortunately. Anova F test is always a right-sided test, and therefore you keep complete alpha on the right tail of the F distribution with corresponding numerator and denominator degrees of freedoms. You reject the null hypothesis if the calculated F test statistic is larger than the critical value. Let me say it again. Anova F test is always a right-sided test. If you know the F test statistic, you can easily find the p-value using your calculator, using the distribution FCDF. Since the Anova F test is always a right-sided test, the p-value is the area to the right from the F test statistic. All right, let's do an example. An experiment was run to determine whether 4 specific firing temperatures affect the density of a certain type of brick. The experiment led to the following data. There are temperature groups and there are density readings. The temperature readings or the temperature groups are not the data. Those are only the group labels. The density readings are the data which we will use in the analysis. All right, so how many groups we have? There are 4 groups. Those are the 4 temperature groups: 100 degrees, 125 degrees, 150 degrees, and 175 degrees Fahrenheit respectively. For each group, density readings are given. We have 4 groups, means the numerator degrees of freedom, or the between group degrees of freedom, should be equal to 4 minus 1, which is 3. Now we need to find the denominator degrees of freedom, or also called the within group degrees of freedom. For that, we have to look at the number of degrees of freedom within each group and sum them up. Here is the first group. That group has 7 readings. That means from the first group, we have 7 minus 1, which is 6 degrees of freedom. Here is the second group. There are 4 data points in it. That means from the second group, we have 4 minus 1, which is 3 degrees of freedom. Here is the third group. There are 4 data points in it. That means from the third group also, we have 4 minus 1, which is 3 degrees of freedom. And here is the fourth group. There are 6 data points in it, which means we have 6 minus 1, which is 5 degrees of freedom from that group. To get the total degrees of freedom, we have to sum up all the within group degrees of freedoms. Then you get 17 as the denominator degrees of freedom. That means we are dealing with an F distribution which has 3 numerator degrees of freedom, also called df1 equals 3, and 17 denominator degrees of freedom, also called df2 equals 17. And here is the F distribution. F distribution is only positive because it models the ratio between 2 chi-squared random variables, which are squared normal variables. Squaring normal variables make chi-squared distribution a positive only distribution, and therefore the F distribution also becomes positive only. If you need more information, you may watch Instructors Chapter 2. All right, to test the hypothesis, we also need F critical value. How can we find it? We said Anova F test is always a right-sided test. Therefore, we keep complete alpha, which is 5% on the right tail of the F distribution. When you do that, we can find that the critical value is 3.2. Well, like I said earlier, the TI-84 calculator doesn't have inverse F function to find the F critical values. Therefore, we have to use the traditional F distribution table. In a traditional F distribution table, you have to match the numerator degrees of freedom, denominator degrees of freedom, and alpha. For the question under discussion, the numerator degrees of freedom, or df1, is equal to 3. The denominator degrees of freedom, or df2, is equal to 17. Alpha is 0.05. Let's go to the traditional F distribution table. Here is the F distribution table. You can see numerator degrees of freedom, or df1, on the very first row. You can see denominator degrees of freedom, or df2, under leftmost set of numbers. For each combination of numerator and denominator degrees of freedoms, we have 4 probability values given: 0.100, 0.05, 0.025, and 0.010. Those are the widely used alpha values. We use alpha equals 0.05, which is the second probability value given. So for the right combination of the degrees of freedoms, we have to read the critical value corresponding to 0.05. For the critical value we need, we have to look under third column, which corresponds to numerator degrees of freedom equals 3, or df1 equals 3. We have to scroll down until we see 17 on the leftmost set of numbers, because the denominator degrees of freedom equals 17, or df2 equals 17. Here is the set of numbers corresponding to df2 equals 17. I have to select the third column and the reading corresponding to 0.05, which is the highlighted value. All right, so the F critical value is 3.2. which means the rejection region of Anova F test for this specific dataset is from 3.20 to positive infinity. Rejection region is right tail only because we do Anova F test only as a right-sided test always. All right, now we have to find the F test statistic. All right, why do we need an F test statistic? We need to test these hypotheses. We will let mu1, mu2, mu3, and mu4 be the true mean densities at firing temperatures 100, 125, 150, and 175 respectively. Then the null hypothesis H0 is all means are equal. The alternative hypothesis H1 is at least one mean is different. All right, all we need now is the F test statistic, which will be later compared against F critical value. You can use your TI-84 CE Plus calculator quite easily for that purpose. We have the data set, so we will first enter the data set. Let's go to the calculator. All right, here is the calculator. In order to enter the data set, you have to go to Stat, Edit, number 1, Edit, hit Enter, and here is the data set. I already entered the data set. We have 4 temperature groups. So I entered all the density readings for temperature group 100 degrees into the list L1. All the density readings for temperature group 125 degrees into the list L2. All the density readings for temperature group 150 degrees into the list L3. And all the density readings for temperature group 175 degrees into the list L4. All right, now we have to run Anova F test for the data entered. For that, you have to go to Stat, select Tests, and then Anova F test is the very last test. You may scroll down using the down arrow key, but also there is a shortcut, that is to use the upper arrow key. Press that, and then you can see H, Anova, and open parenthesis. Select that, and then hit Enter. Now you can see on the screen Anova, open parenthesis. There you have to define the list labels where you entered the data. We have 4 groups, and we entered the data from those 4 groups into the lists L1, L2, L3, and L4 respectively. Therefore, we have to define them as that separated by a comma. First list is L1, second 1, and then enter a comma, and then second 2, which is the list L2, comma, second 3, which is the list L3, and separated by a comma again. Second and 4, list L4. All right, that's all the lists where we entered the data. We have to now close the parenthesis and then hit Enter. The calculator output has plenty of stuff. For the moment, look at only the first 2 lines of the calculator output, which indicate the F test statistic and the p-value. The calculated F test statistic is 2.4527. And it's not in the rejection region, which means we accept the null hypothesis H0. Accepting the null hypothesis means the data do not support the alternative. Now we have to interpret the test result. Interpretation should always be only about the fate of the alternative hypothesis. Since the data did not support the alternative, we interpret it as we do not have statistical evidence with 95% probability to conclude that at least one mean is different from the other means. Why 95%? That's because the rejection region was for alpha equals 5%. Specifying the probability of the decision is required for the complete interpretation. All right, this is the test statistic critical value approach. What if I need the p-value? Like I said earlier, the Anova F test is always a right-sided test. This means the p-value is the area to the right from the test statistic. According to the calculator output, the p-value is 0.0986. You must also know how to calculate the p-value, of course, using your calculator TI-84 CE+, if you are given only the F test statistic, numerator degrees of freedom, and denominator degrees of freedom. For that, you have to go to distributions, select FCDF, input lower limit, upper limit, numerator degrees of freedom, and denominator degrees of freedom. For this question, The test statistic is 2.4527. Therefore, the lower limit should be 2.4527. For the upper limit, enter something positively large, such as 100,000. And the numerator degrees of freedom equals 3. The denominator degrees of freedom equals 17. And that should give you the p-value of 0.0986. Please try it yourself with your calculator function fcdf and see if you can get the same p-value. This p-value is larger than 0.05, the alpha value. As always, the p-value method accepts the null hypothesis when the p-value is larger than alpha. Of course, 0.0986 is larger than 0.05. Therefore, we accept the null hypothesis. This means we get the same answer as earlier. All right, that's basically it about the Anova F test. All right, now we will look at the calculator output a little bit further. All right, I enlarged the calculator screen. F test statistic is given on the first line. We already used it. The p-value is given on the second line. We already used that too. Then you can see the term factor. Factor means groups. MS Excel uses the term groups. TI-84 uses the term factors. Under factors, you can see df equals 3. That's the between group degrees of freedom because we had 4 groups or 4 factors. Sums of squares and mean squares are also given. Then if you go down, you can see the term error. The error means within groups. MS Excel uses the term within groups. TI-84 uses the term error. Of course, within a specific group, the reason why all the observations are not identical is because of the error. So both terms are scientifically correct. Under error, you can see df equals 17. That's because we had 17 degrees of freedom within groups. Sums of squares and mean squares are also given. All right, that's basically about one-way Anova F test. Thanks for your class participation. Have a nice day.